2.5, so we've got that covered. And so here we go. This is the last bit of topic that we have for this unit. Okay. And let me just start off by saying that in section 2.4, our problems looked like this. We looked at the limit as x approaches a of f of x, and we said, we looked at the instances where this came out to be either arbitrarily large positive or arbitrarily large negative. Okay? I've tried to keep section 2.4 and 2.5 separate so you had enough time to absorb 2.4 prior to moving into 2.5. What's critical that you understand here is what is approaching a finite number in this problem?
Y?
No,
Basically.
not y. A finite number, a fixed number.
Oh, X.
Yeah. So what's going on here? As the domain values approach A, the range values does what? Gets large. Okay? It's critical that when you're looking at this limit notation that you're able to see where are the domain values going, where are the range values going, and keeping track of those. Okay? Because here in 2.5, we're going to look at the limit as x approaches infinity of f of x, and we're going to say that that's something like L in some cases. Not always, but in some cases. So what's going on here? As the domain values do what? They get what in this problem?
Large.
They get large. As the domain values get large, do the range values approach some number L? Okay? So this is how you've got to keep track of these two different types of issues. Okay? Because we use different techniques in different types of problems. All right. So that's actually the summary of this entire lesson. Okay? But let's actually jump into it. Here I want to look at the graph of this function right here. F of x equals x squared minus 1, all divided by x squared plus 1. Okay? First of all, let's ask this question. Does this function have any vertical asymptotes or holes? Peyton, you're shaking your head.
No, I don't believe so.
Why not?
There's no hole because nothing cancels out, correct? When you
Okay. Why? But how about why are there no vertical asymptotes?
because the range is infinity, correct?
I don't know if the range is infinite.
Because nothing makes x squared equal -1.
Yeah. What's the domain of this? What's the domain of this function? What am I allowed to plug into this function? The domain of this function goes from minus infinity to infinity, right? There is nothing, because the only operation that could potentially get me into trouble is what?
-1.
No. What operation? Operation. Multiplication, addition, square rooting. What am I doing that could get me into trouble?
Division.
We're dividing. So I've got to make sure I don't divide by what? 0. What would make the denominator 0? I don't think so. What's -1 squared?
Well, yeah. And if x squared was -1, but that's not possible.
Ah, okay. If x squared came out to be -1, but what number when you square it gives you a negative? No real number. Okay? So there is no number that would make the denominator in this expression 0. Okay? And so let's just do a couple of things. What is f of 0? Let's find the y-intercept. The y-intercept is -1. Everyone okay with that? Okay. Let's find the zeros of this thing. How do you find the zeros of a function? You set the function equal to 0, right? Well, that happens when x squared minus 1 over x squared plus 1 equals 0. What is the kind of the general form of the expression on the left there? It's a fraction, right? When is a fraction 0?
When the numerator equals 0.
When its numerator is 0, right? So that happens when x equals plus or minus 1. That's when the numerator is 0. Okay. So putting that information in here, okay, here's the y-intercept of 0, 1. Here are the x-intercepts, the zeros of the function at -1 and 1. This has no vertical asymptotes or holes. Okay. Here's a question for you. What happens when I plug 10 into this function? What do I get out? Let's actually evaluate that. What do I get out when I plug 10 into this function?
99 over 101.
Yeah, if we plug in 10, we square it, we get 100. Minus 1, we get 99. If we plug in 10 into the denominator, square it, we get 100. Plus 1, that's all over 101. How are we doing, folks? Okay. What's that number close to? 99 over 101, what's that close to? It's close to 1. And in fact, if I plugged in 1,000, I'd get something what? Even closer to 1. Okay? So the graph of this function looks something like this. So what I want to talk about now is what we call the long-term behavior of the graph, meaning away from 0. How is this function behaving? Away from 0, how is this function behaving? Well, let's find out. Remember in previous classes we'd say that this has a horizontal asymptote at y equals 1? Okay. We want to somehow encapsulate that with limits. We want to use limits to be able to describe this idea. Okay? So here we go. This is what we say. If as x becomes arbitrarily large, f of x gets arbitrarily close to L, meaning as x approaches infinity, f of x approaches L. How do we write that in limit notation? We will write the limit as x approaches infinity of f of x equals L. Okay. In this second statement here, as x becomes arbitrarily large but negative, if as x becomes arbitrarily large and negative, f of x becomes arbitrarily close to L, meaning as x approaches negative infinity, f of x approaches L. How would we write that in notation? Oh, we can answer this one. I have you guys do jumping jacks before class. How do I write this?
Same thing, but negative infinity.
Same thing, except for our limiting value is going to be negative infinity. Okay? So for f above, by above I mean in number 1. In number 1, what would we write here? Yeah, we'd say as x goes far to the right, as the domain values get large, what do the y values get close to? What do the range values get close to? And we see, as we go further and further to the right on this graph, the y values are getting closer and closer to 1. So how do we encapsulate that with limit notation? Using this expression here. Now this is not truly a limit the way we originally defined limits. Because we originally defined limits for domain values approaching some fixed number here. But this notation is powerful enough to also take on this idea too. Okay? So if as the domain values get large, as the domain values get large, we find that the y values approach 1. Okay, let's read that together. As the domain values get large, the y values approach 1. All together, one more time. As the domain values get large, the y values approach 1. Okay? Do you see that these limits make a lot more sense if you read them aloud? Does that make sense? So practice doing that. Okay? If you see LIM x arrow infinity f parentheses x close parentheses equals 1, if that's how you're saying that to yourself, you're never going to fully grasp the notation. Okay. All right. What do we find here? As the x values go far to the what? To the left, what do the y values appear to also be approaching? 1 as well. Okay. Okay. So if as x gets large to the right, we approach L, or if as x gets large to the left, we approach L, or both, then we say that the line y equals L is called a what? Horizontal asymptote. Okay? All right. So go ahead. I'd like you to do number 5. You've got all the tools you need for number 5. Make sure that for your vertical asymptotes you write x equals. Make sure that for your horizontal asymptotes you write y equals. Okay. So in your groups, go ahead and fill that in. Okay. Folks, so be careful. The limit proper, make sure you have that the limit proper as x approaches 2 does not exist. Even though the right-hand limit and the left-hand limit, well, they don't exist either, but we can describe how they're behaving. We can't describe the limit proper. Okay, at 2. Okay, but notice that even though the limit proper didn't exist, either the right or the left-hand limit gave us infinity, so that's enough to say that we have a vertical asymptote at x equals 2. Okay, folks, because I need to know that you know what's going on, you have to give these asymptotes in equation form. You must write x equals -1 or y equals 4. If you tell me there's a vertical asymptote at 2, that's true, but I don't know if you know what you're talking about. Right? Because there's also a horizontal asymptote at 2. Does that make sense? Okay, so you need to give it to me in an equation form. Okay. Unfortunately, vertical asymptotes has the word asymptote in it, and horizontal asymptotes has the word asymptote in it. And so that leads a lot of people to believe these two ideas are related to one another, and they're not really related to one another. Okay? It's essential to realize that vertical asymptotes arise from exclusions in the domain of the function. Okay? So vertical asymptotes arise from exclusions in the domain of a function. Now, just because the function's undefined at, say, x equals 7, doesn't mean I'll have a vertical asymptote there, but I might. So I need to go explore what's happening around 7. Okay? But the vertical asymptotes, in fact, let's say this, vertical asymptotes and holes arise from exclusions in the domain. So vertical asymptotes are more related to holes than they are horizontal asymptotes. Okay? What do the horizontal asymptotes have to do with? They have to do with the long-term behavior. So if a vertical asymptote describes the behavior near where a function's undefined, can a graph ever cross a vertical asymptote? Can you ever have a point on a vertical asymptote? No, because it has to do with where the function's undefined. But unfortunately, students somehow, somewhere down the road, got the idea that graphs cannot cross horizontal asymptotes. Okay? A lot of people think that. Okay? You pull people on the street. A lot of people think that. Okay? But they're wrong. Graphs can cross horizontal asymptotes. Does this graph cross the horizontal asymptote at y equals 4?
Yes.
Here's the horizontal asymptote at y equals 4. Does it ever cross it? Sure, it crosses it here, it crosses it. Is that a problem? No. All we're saying is that as we go further and further to the right, the y values are getting closer and closer to 4. That's all we're saying. In fact, does the line, let's say this, does the line y equals 1 have a horizontal asymptote? Yeah, what does the graph of this function look like? Here it is, there's its graph. Does that have a horizontal asymptote? Yes, it does. At y equals 1, it has a horizontal asymptote. It's not very, you're not learning any new information by describing the horizontal asymptote for this function. Okay, but it has a horizontal asymptote there. Does it ever cross it? Oh yeah. In fact, it's on top of it the whole way. Okay? So be careful with that. Horizontal asymptotes are just a way of describing the long-term behavior of a graph. And in fact, if you jump to the next page, does this function have a horizontal asymptote? Yes, it does. Where's this horizontal asymptote at? What's the equation of it? Y equals 2, I think. Okay. Because why? The further and further I go to the right, the closer and closer the y values get to 2. And the further and further I go to the left, the closer and closer the y values get to 2. So we've got a horizontal asymptote at y equals 2. Does this graph ever cross its asymptote?
Lots.
Many times. all we're saying is that, notice that eventually pick any window, and this gives us an insight to where we're going to go in section 2.7, pick any window around that horizontal asymptote, and although initially not all y values are in that horizontal asymptote, eventually the graph is completely inside that window. Okay? Because I can make that window as small as I want, then we know we've got a horizontal asymptote. As long as I put that window centered about 2, I can make it as small as I want, and it always, as I go far enough to the right, the graph will be contained in that window. I can do that for anything, so that's why we have a horizontal asymptote there. Okay, if you missed that explanation, that's okay. We're going to do that more. Oop. We're going to do that more in section 2.7. Okay? I saw a question, or I thought I did. Somebody looked like they were going to ask a question. Come on, folks. You paid good money to be here today.
I guess
Yes?
my question, I feel like I already figured it out, was if sine of x would have a vertical, not vertical, horizontal asymptote of 0, but then you said that it doesn't, was explained further that it has to get smaller, and so it would.
Oh, this graph does have a hole in it.
Yeah.
It does have a hole. It has a hole right here at the order pair 0, 6. You can't see it from the picture.
It wasn't quite related to this problem.
Okay.
I already kind of figured out the answer though.
Okay, we'll look at it going forward. All right, so I want to put some graphs up on the board that I think are elementary graphs. You absolutely need to know, especially A and B. Okay? Somebody should be able to shake you up from an afternoon nap and say, graph 1 over x. And you should be able to graph it just like that. And then say, let me go back to sleep or something. But you need to know this graph without thinking. Okay? You need to know it that well. Okay? So what does the graph of 1 over x look like? It is the reciprocal function. Its graph looks something like this. Okay, notice how I just graphed this. I put on it the 2 ordered pairs that I knew. What's the reciprocal of 1? 1. What's the multiplicative reciprocal of negative 1? What is the reciprocal of 2? And you could plot this thing. What is the reciprocal? What's the reciprocal of 1/10? 10. What's the reciprocal of 1/1000th? 1,000. The closer and closer I get to 0 from the right, what happens to my y values? What's that?
Goes to infinity.
Yeah, the y values get arbitrarily large as I get closer and closer to 0 coming from the right. Okay? So this graph has both horizontal and vertical asymptotes. We find the vertical asymptote by exploring the behavior near x equals 0. We find the horizontal asymptotes by looking at the behavior as x gets large, either large positive or large negative. Okay? What does the graph of 1 over x squared look like? We graphed this just the other day. The graph of this function looks like this. Okay? What does the graph of 1 over x cubed look like? Well, when I plug in a 1, what does it spit out? 1. If I plug in a large number like 100, cube 100, how big is that? Big. Divide that into 1, what do you get?
Still big?
No.
Still the same?
No?
Very, very small.
Small number, right? If I have 1 candy bar and 10 cubed friends, they're not getting very much, right?
I disagree.
So as I go further and further to the right, my y values get very, very small, approaching 0. What if I approach 0, though? What's 1/10 cubed? Very, very tiny number. What's 1 divided by 1/10? Even tinier. This goes up like this. Okay. And sure enough, this is the graph of the other one. Folks, how does the graph of 1 over x look like the graph of compare to the graph? How do the A and C compare? They look similar. Are they the same? No. Okay. Specifically, that green function rises up more quickly as we approach the asymptote, and it dies off more quickly. It goes to 0 more quickly. Okay? But the general shape of those two functions is the same, and that's what I want you to notice going forward. Okay? What do you think the graph of 1 over x to the 4th looks like?
Similar to B.
Yeah, so it's going to be similar to b. Not exactly the same. Okay? It's going to rise up more quickly and die off more quickly. Okay? But there's the graph of 1 over x to the 4th. Okay? So use these functions as sort of your basis. Oh! Ooh, somebody's looking at me funny. Is it Veronica? You're looking at me funny.
I'm good.
Oh, I would be looking at me funny right now.
Yeah, it's not.
Yeah, this isn't. There we go. Thank you.
Everyone was like, wait.
Okay, what does the graph of 1 over x to the 4th look like? It looks like the graph of 1 over x squared. I made a mistake putting it up there. Okay. All right. Did everyone get that? Okay. All right. So here's some basic facts. Some of these we've already seen. I'm trying to put both the 2.4 and 2.5 facts together on one page, just so you can contrast them. Okay. So let's say I have a natural number and I've got 1 over x raised to a natural number. Then this graph has a vertical asymptote at x equals 0. Do you agree? When I look at the limit as x approaches 0, I will either get infinity or minus infinity depending on my direction of approach and depending on the function. Okay? In fact, if n is even, like 1 over x squared or 1 over x to the 4th, then as I approach 0, I'm always going to get what, regardless of the direction of approach? Positive infinity. We always get an arbitrary large number. But if the function is odd, then I'm going to get out either infinity or minus infinity, but the direction of approach matters, right? As I approach 0 from the right, I get out positive infinity, but as I approach 0 from the left, I get out negative infinity. So that's all that's being summarized in that statement right there. Okay? As a reminder, we can remember these above limits by the phrase 1 over a small positive number approaches infinity, and 1 over a small negative approaches negative infinity. Okay? Now, this is just a recap of section 2.4. Okay, that's what we did, that's what you've been working on. Okay. The new material is here. If I just have 1 over x to the r for any rational number r, okay, as x gets large, where do the y values get close to? Well, we'll have a horizontal asymptote. Where will it be? Folks, I don't know what I'm doing wrong. I'm getting looks from you. If I have 1 over x to the 3rd and I plug in a big number for x, what am I going to get?
Small number.
Something that's getting close to
0.
0. Okay? So if I put 1 over x to the r, and I say I'm going to plug in a big number for x, what am I going to get? A small number, something that's approaching 0. That's all I'm saying here. Okay? So as x approaches infinity, or as x approaches negative infinity, that expression tends towards 0. So that gives me a what? Horizontal asymptote. Okay? All right? Now, we can take this one step further by saying, hey, not only, it doesn't even have to look like 1 over x to the r, it could be some shifting of that expression too, and it'll still go to 0. So this statement here, I know that looks a little confusing. What I'm saying is if I asked you what's the limit as x approaches infinity of, say, I don't know, 2 over 3x to the r, let's say 2 over 3x to the 7th minus 6, what's that going to approach?
0.
It's going to approach 0. You can use that fact. That fact, you can just go ahead and say, I know that to be 0, because it's just based on a transformation of these elementary graphs. Okay? Because this function right here that I put up, this function right here, is just a transformation. It's just a combination transformation of those elementary graphs. So it's still, as you plug in large numbers, still has a horizontal asymptote at y equals 0. Okay? All right, so we remember this phrase by 1 over a large positive number approaches what? 1 over a large number approaches what? 0. And 1 over a large negative approaches what as well? 0. Doesn't matter if it's positive or negative. Okay. Okay, folks, so here's our trick for dealing with limits at infinity. Okay? I'm not going to hold you responsible for this preposition issue, right? But the title of section 2.4 was infinite limits, meaning when we took the limit, we got out infinity. The title of this section is limits at infinity, meaning the domain value is approaching infinity. It's because the domain value is coming large. So anyway, when you deal with limits at infinity, okay, i.e. when you're looking at the limit as x approaches infinity of f of x, the trick to dealing with this is to multiply by 1 over x to the highest power seen in the denominator. One over x raised to the highest power seen in the denominator. Okay? Over itself. I guess we'll stab that. Okay? So I want to skip 16. I want to come back to 16 here in a minute. 16 is going to be kind of the single most important example from this section. Okay? But we'll skip it for just a second. Are there any questions on that? You guys are writing this down. Saying, why the heck is he so grumpy today? I'm not. All right. So let's look at this problem here. Okay? All right. For number 17, you should have learned in college algebra a way to determine the horizontal asymptote for this function. Some point in college algebra, you learned some tricks for this. You are welcome to use those tricks. I'm going to do it the calculus way. The calculus way for this problem is harder. Okay? You are welcome to use your college algebra tricks, but know that the college algebra tricks won't apply to number 16 here. You have to use the calculus tricks on number 16. So what type of, if I was going to ask just one question on the test, which one would I ask? 16, not 17. Okay? So it may be that you're looking at this and you say, aha. You might remember the trick. You might say, aha, I remember that there's a horizontal asymptote at y equals 3/5. That's great. And you can write that down if that's all I'm asking you for in this question. Okay? But I'm going to use the calculus techniques. It's easier to do the calculus techniques on this problem than it will be on number 16. So we're going to practice them here to learn it. Okay? So this is not an infinite limit. This is not a 2.4 question. This is a 2.5 question. How do we know that? Because what's happening? The domain values are getting large, not the range values necessarily. We're looking at the limit as the domain values get large. So what's our trick for limits at infinity? This one weird trick, right? It's on the previous page. What's our one weird trick?
Multiply by 1 over x squared.
We're going to multiply by 1 over x raised to the highest exponent seen where? In the denominator. Okay? So we're going to do 1 over x squared divided by 1 over x squared multiplied to 3x squared minus x minus 2 all over 5x squared plus 4x plus 1. Okay? Why am I doing this trick? Well, it turns out it works. If you want to know more about it, come by and see me. We'll talk about it. Okay? So now what I'm going to do is I'm going to distribute this 1 over x squared to each term. Okay? I'll do it this first time through in gory detail. So this will be 3x squared over x squared minus x over x squared minus 2 over x squared. Distributing that 1 over x squared to all three terms in the numerator. Now we'll distribute that 1 over x squared to all three terms in the denominator. Okay. You are welcome to skip this step, and I usually do. Okay. This leaves us with the limit as x approaches infinity of 3 minus 1 over x minus 2 over x squared, all divided by 5 plus 4 over x plus 1 over x squared. Okay?
Why is there 2 lines for the division?
I like to do double lines when I have other fractions, when I have fractions inside of fractions.
Okay.
Uh-oh, did I restart this? Yeah. I like to, when you have, this is a fraction and I've got and this is a fraction and it's separated by a larger fraction. Division is actually not associative, so you can't group division every way you want. And so you need to understand that this is the larger division problem, and that this is, by grouping, this is inside of the other two. So it's not a big, you don't have to do it.
Okay, I was
Yeah.
just wondering if there was like
Yeah,
this.
but if you look sometimes at books when they have what are called complex fractions, they will put a bold bar for the bigger fraction bar, but I can't do bold, so I do a double underline. Yeah, yeah, you don't have to worry about that. Okay. This next step is again one that you don't usually need to show, but I'm going to show it to you the first time through. Okay. I'm going to distribute the limit to both the numerator and the denominator. Can I always do that? No. Only if the underlining limits all exist. Okay? Then I'm going to distribute the limit over the sums and differences. Can I always do that? No. Only if the underlining limits all end up to exist, which they will, but just know that this move is, I'm only doing it because I know when I'm done it will work out. Okay? So here we go. We get the limit as x approaches infinity of 3 minus the limit as x approaches infinity of 1 over x minus the limit as x approaches infinity of 2 over x squared. All divided by the limit as x approaches infinity of 5 plus the limit as x approaches infinity of 4 over x plus the limit as x approaches infinity of 1 over x squared. Okay? You do not normally have to write out this step. Okay? But I'm just showing it to you so you can see what's happening behind the scenes here. Okay? Does everyone understand what I just did? Okay. Now, if let's say one of these limits came out to not exist, what does that mean? It means that this step, it was an illegal step. Okay? Or if my denominator came out to 0, what would that mean? It would mean that this distributing over the numerator and denominator was an illegal step. Okay? All right. So this is usually what I do is I usually go from this step 1 to this step 2 to this step here 3. Okay. Usually I skip that step. I don't write that one out, and usually I don't write this one out. You don't need to either, but it's good to see what's going on. Okay. All right. Let's go through and analyze each one of these limits. This is the limit as x approaches an arbitrarily large number of a constant. What is the limit of a constant?
The constant.
Yeah, it's just the constant. So what do I get? I get 3 minus. What is the limit as x becomes arbitrarily large of a reciprocal function? It's 0. That's just a previous page. That's just what we said right here in 12 and 13. We said, regardless of what that exponent is, as x gets large, it goes towards 0. So this is 3 minus 0. How about this limit here? It's also 0, right? Minus 0. All over 5. What's this limit here? Plus 0. Plus 0. What am I left with? 3/5. So I didn't ask you to do it, but what did we just show? We just showed that we have a horizontal asymptote at y equals 3/5. Okay. Now, in college algebra, they went ahead and gave you the result of doing this limit procedure without actually having you do the limit procedure. So at some point you learned, hey, if the degrees of the numerator and denominator are the same, then you look at the ratio of the leading coefficients. Do you see that you would have gotten the same answer without any of the headache? Okay, great. But can I ask you questions where you have to use this technique? Yes. So you should practice the technique on these easier problems first, so you get comfortable with it, so that then when I ask you this hard problem that we're about to do, it's not so bad. Okay? All right. Let me see here. Is there something else I want to look at? No, not yet. Yeah. So let's do number 23. This is a couple pages out. I want to practice this one more time. Okay. So let's look at the limit as x approaches infinity of x squared plus x over 3 minus x. Okay. Again, you might remember the college algebra techniques to this. Okay. But we're trying to look at this in terms of we're trying to analyze whether we have a horizontal asymptote or not. Okay. Are we going to have a horizontal asymptote? What do you think? Folks, what's happened to my numerator? It's getting large positive. What's happening to my denominator? It's getting large negative. It's a tug-of-war match. It's a tug-of-war match, right? One's getting big. The thing when the numerator gets larger, the fraction gets larger. When the denominator gets larger, in the absolute value sense, the fraction gets smaller. It's a tug-of-war match. Okay? Who's going to win? I don't know. You might know in this case, but in other cases it might be something different. Okay? So, we're going to analyze this by looking at the long-term behavior, okay, using our trick. Okay? But maybe you remember, hey, if the degree of the numerator is more than 1 above the degree of the denominator, 1 or more, then you're not going to have a horizontal asymptote. Yeah, then you're not going to have a horizontal asymptote. Maybe you remember that. If not, that's okay, because we've learned the better calculus technique for doing this anyway. Okay? So, this is equal to the limit as x approaches infinity. What's my trick here? What's the one weird trick that gets us through this? We're going to multiply this by 1 over x raised to the highest exponent seen in the denominator, which is what in this case? 1. So we're going to multiply this by 1 over x divided by 1 over x. When we do so, we get the limit as x approaches infinity of, now I'm going to distribute, and I'm left with x plus 1 all over 3 divided by x minus 1. Okay. All right, so this is our first time encountering this. This is a 2.4, 2.5 combo problem. What's happening to my numerator? It's becoming arbitrarily large. What's happening to my denominator? It's approaching -1. Does everyone see why it's approaching -1? Because this term is going to die off as x gets large, right? So the denominator is approaching -1. The numerator is approaching an arbitrarily large positive number. So we get that this limit comes out to be -infinity. Folks, this is the first time. So this is what I mean by 2.4, 2.5 combo problem. It's a 2.5 problem because we're looking at limits at infinity. The domain values are getting large. As the domain values gets large, what happens to the range values? They become arbitrarily negative. Arbitrarily large negative. Okay. Questions on that? I don't know. I'm having a hard time reading the room, folks. Do you have any questions? Do you want more examples of that? Fewer examples? You knew all this?
It's fine.
All right. Okay. Let's do one more, just for fun. So let's do this one here. So I'm on page 8, question number C. So all I want to look for right now is the horizontal asymptotes. So we're going to look at the limit as x approaches infinity of x cubed minus 2x squared minus 8 over x divided by x to the 4th minus 64x. Okay, we're going to do this one a little bit faster. What is my trick here?
1 over x.
We're going to do 1 over x to the what power, folks?
4.
1 over x to the 4th. Okay. That gives me, when I distribute, 1 over x minus 2 over x squared minus 8 over x cubed, all divided by 1 minus 64 over x cubed. Now we'll go ahead and evaluate this. Okay, so in my head, what I'm doing is I'm distributing the limit to the numerator and the denominator, and I'm distributing the limit all the way across the numerator and all the way across the denominator. This is going to give me 0 minus 0 minus 0 all over 1 minus 0. What do we end up with? 0. So what did we just show? We have a horizontal asymptote where? Yeah, how do we want to write it though?
Y equals 0.
At y equals 0. They're horizontal, so they're y equals. Right? Okay. Folks, right here on question 28, I summarized the rules that you learned in college algebra, except I did so incorrectly. So let's correct them. Okay. So all of these inequalities are going the wrong way. Okay. So the first one says if the degree of the numerator, which is m, is larger than the degree of the denominator, you're always going to end up with what? A horizontal asymptote where? Y equals 0. Did you see that on that last problem? What's the degree of the denominator? 4. Degree of the numerator was 3. In the tug-of-war match, who won out? The denominator. It brought everything down to 0. Okay. If the degree of the numerator is smaller than the degree of the, if the degree of the numerator is larger than the degree of the denominator, then we have no horizontal asymptote. Okay. If we have time, we'll come back and talk about oblique asymptotes, but for right now, I'm just skipping the issue. Okay. But what if the degrees are the same? That was our first example, right? You could just look at the ratio of the leading coefficients. Okay? You are welcome to use these college algebra rules. That's perfectly fine. Okay? I've just done 3 problems, though, the hard way, because I wanted to make sure you learned the calculus way of doing this. That's going to help us now when we go all the way back to question 16. Okay? All right. I'm definitely going to run out of room on question 16, so I'm going to just put it on another page. Okay. We're asked to find all asymptotes to this function. Okay? All asymptotes. So what do I mean? Vertical asymptotes and horizontal asymptotes. So let's first go hunting for vertical asymptotes. How do we find vertical asymptotes? Well, vertical asymptotes arise from what?
Domain.
Problems in the domain. Okay, let's do that again. Vertical asymptotes arise from problems in the domain. Okay. What's the domain of this function? Okay, what operations am I doing that could get me into trouble? Division and potentially square rooting, right? Let's tackle the square rooting first. I got to make sure I don't take the square root of a what? Negative number. But let's look at the expression inside the radicand there. It's always going to be positive, right? Because of it's 1 plus either 0 or 1 plus a positive number. So the radicand's always positive. So even though the square root is potentially a problematic operation, it's not in this case. What's the other operation that can get me into trouble? Division. We got to make sure we don't divide by 0, which means x cannot equal, what is that, 5/3? Right? What's that?
Can't it also not be smaller than that?
Why not?
Because it's -5, so like, for example, if x was 1, like...
Okay, we'd have 3 minus 5, we'd have a -2 in our denominator.
Oh.
Is that a problem?
No, sorry.
No, you're asking the good questions, right? We're asking the right questions, okay? But it's for the square rooting that we need to make sure that we're not taking the square root of a negative number. But for division, we only need to make sure that we're not dividing by 0. We can divide by negative numbers, okay? All right. So if we're going to go looking for vertical asymptotes, who are our candidates to test? Our candidates are the exclusions in the domain. Now, just because 5/3 isn't in the domain, does that mean I have to have a vertical asymptote there? No. I could have a hole there. Okay, so we have to go look. So let's look at the limit. As x approaches 5/3 of the square root of 2x squared plus 1 all over 3x minus 5. So we're exploring the problem in the domain to look for vertical asymptotes. This is a 2.4 question, right, folks? It's a 2.4 question. Okay. What's my denominator approaching? 0. What's my numerator approaching? Some positive number, right? So this is a 2.4 question. Because the denominator is approaching 0, the numerator is approaching a positive number, I better pick a direction of approach. When I plug in a number a little bit bigger than 5/3 and then multiply it by 3, I've got something a little bit bigger than?
Bigger than 5.
A little bit bigger than 5. Then I subtract 5 from it, so I've got something a little bit bigger than 0. I've got a positive number divided by a very, very small but positive quantity that's tending where? Towards positive infinity. Okay. What if we go the other way? The limit as x approaches 5/3 from the left of the square root of 2x squared plus 1 all over 3x minus 5. Where's that heading? Negative infinity. Okay. Why? Because I'm plugging in a number a little bit below 5/3. So when I multiply it by 3, I've got a number a little bit below 5. And when I subtract 5 from that, I've got a very tiny negative number. Divided into, notice the numerator is always positive, as we discussed. Questions on that, folks? Okay, so based on that, what can we say? We can say we have a vertical asymptote where? At x equals 5/3. Okay. Did I have to check both directions to say there was a vertical asymptote there? No, it was enough just to find out that one of the two came out to be infinity, but I checked both anyway. Okay, that was a 2.4 question, folks. That's a review. Okay, are there any questions on that? We sure? I had a student come to me in my night class the other day and said, "Thank you for asking me the question when you knew I didn't know the answer, because you kind of talked me through it, and I was able to figure it out." I don't know. That sometimes works. If you're lost, let me know, and I'm going to ask you some good questions. Or I'll try to anyway. No? Okay. Moving on. So now we want to go hunting for what? Now what should we go hunting for? Horizontal asymptotes. Okay? So to do horizontal asymptotes, we look at the what of the graph? The long-term behavior or the end behavior of the graph. We're going to look at the long-term behavior. So let's look at the limit as x approaches infinity of the square root of 2x squared plus 1 all over, was it 3x minus 5? I think so, 3x minus 5. Okay? Now, what's my trick? Yeah, everyone write down the next step, please. You should all be able to do the next step. If you can. Everyone okay with that step? Okay. So far, it's looking exactly like all the previous problems, right? Okay. So before I finish this, I want to actually go to another page and just remind you of a fact. Way back when, if I asked you to simplify the square root of 72, what would you do? Well, you could rewrite that as the square root of 36 times 2, right? And then you said, oh, but by using my radical properties, my product properties of radicals, I could rewrite this as 6 square root of 2, right? Everyone okay with that? So now I want you to think of going this way. If I take 6 times the square root of 2, if I want to put that 6 inside the radical, how's it going to go in? So it's going to go in as the square root of 6 squared times 2, right? Does everyone see how I passed it in there? So, this is very important. If x is positive, if I take 1 over x and I want to pass it inside that square root there, how's it going to go in? 1 over x squared, right? Everyone okay with that? When you pass something inside of a square root, it becomes squared. Okay? Now, what's 1 over x quantity squared? How could I write that? That's the square root of 1 over x squared. Everyone okay with that? Times 2. And then I could move on from there. Okay? But this is this hard step that I want to make sure everyone learns. When you pass something inside a square root, it comes in as a quantity squared. Okay? Now remember, 1 over x quantity squared is just 1 over x times 1 over x, which is 1 over x squared. So I don't actually need the parentheses around the whole thing. I can just write the squared in the denominator because the numerator is 1. Okay? Question?
Is it only applicable if x is greater than 0?
Correct. Let's go the other way. Okay? So what about if x is negative? Okay? Well, before we do that, let's look at this example here. If I want to take negative 6 square root of 2, and I want to push that negative 6 inside the square root, one way you could think about saying, okay, well, there's the negative 6 quantity squared times 2. Everyone see that? I brought it in and I did what with it? Squared it. But here's the issue. What was the sign on the original expression? Negative. It's a negative value. What's the sign on this value? Positive. So what needs to come out here? I need to put a negative sign that's there. Even though I passed that negative 6 inside the square root, I need to put a negative sign in front of the square root. So, if x is negative, if I know that x is negative, and I want to look at 1 over x, square root of 2, what is the sign on 1 over x? What's the sign on 1 over x?
Negative.
Negative, right? If x were negative 3, then what's 1 over x? Negative 1/3. So even though I don't see this is really important though. Do you see the minus sign? No, you don't see it, but you know x is negative. So you don't see the minus sign here. So when I bring this in as 1 over x squared times 2 all inside the square root, what do I need to put here? negative sign. Folks, that is a very subtle and complicated step. Okay. We're having a hard time seeing it. Okay. Are there any questions on this? Okay. I will test you on this step. Okay. It'll be on the first exam. It'll be worth 5 points. Okay. Not 5 points for just the one step, but the problem is a whole will be worth 5 points. Okay. This step itself probably worth 2. Okay. But this will show up. Okay. So back to finding the horizontal asymptotes. Okay. We're currently looking at the long-term behavior to the what way? To the right, correct? Because we're approaching positive infinity, right? Okay. So I'd now like to pass this 1 over x inside the square root. When I do so, it comes in as 1 over x squared. And over here, I get 3 minus 5 over x. The denominator seems kind of familiar. It's kind of what we've been doing. Okay? Does everyone see what I did in the numerator there, though? Okay. So then we clean this up. We get the limit as x approaches infinity of the square root of 2 plus 1 over x squared all over 3 minus 5 over x. So now I'm ready to run through this procedure that we've been doing, right? Okay. So we distribute the limit to the numerator and the denominator. Can I always do that? No. Provided the denominator doesn't come out to be 0 and the limits all exist, I can't. Then I'm going to pass the limit through the square root. Can I always pass a limit through a square root? No, providing the radicand is never negative and the limits exist. Then I'll do some more distributing, etc. Eventually I end up with the square root of 2 plus 0 all over 3 minus 0, which gives me the square root of 2 over 3. Any questions on that? Okay. Folks, with these square root problems, I know maybe you could have looked ahead and say, I'll guess what the answer is. When I write these square root problems, you cannot look ahead and see what the answer is, generally. You have to do this procedure. The college algebra techniques won't help you. You can't say ratio, leading coefficients, whatever. You can't use those techniques. So you have to do this procedure. Okay? So that was the horizontal asymptote to the right. We looked at the right long-term behavior. Now what do we need to look at? The left. So we're going to start over. We'll look at the limit as x approaches infinity. Oh, excuse me, of, not infinity, but what? Negative infinity of the square root of 2x squared plus 1 all over 3x minus 5. So our first trick is the same, right? We do 1 over x divided by 1 over x. Okay? Now, let's go ahead and distribute in the denominator first. This gives me 3 minus 5 over x. We should be feeling okay about that step, right? Anyone want to talk about that? All right. What is x approaching here? Negative infinity. So eventually x is going to take on what values? Negative values. So what does that make the expression 1 over x? It's a negative expression, right? So I'm now going to pass 1 over x inside the square root. I'll pass it inside the square root this way. Right? Just as I did before. But what do I have to do here? I have to retain the fact that this factor right up here is negative. So I put a negative sign in front of that square root. Folks, that's the hardest step of this unit, in my opinion. This is the hardest problem of this unit. Okay, there's a lot of subtle steps happening here. Okay. Now we can go ahead and just finish this out just as before. This gives us the limit as x approaches negative infinity of negative square root of 2 plus 1 over x squared, all over 3 minus 5 over x. I think I did that right, yep. So this gives us evaluating now through, essentially through direct substitution, right? It's not truly direct substitution, okay, but we're ready to say we distribute the limits everywhere. These that look like 1 over x to a power go to what? Zeros, and everything else is constants, right? So we're left with minus the square root of 2 plus 0 over 3 minus 0, which gives us minus the square root of 2 over 3. Folks, these will not always just be opposite of signs from one another. I just didn't give you too hard of a problem to start off with. Okay? Usually there's more happening in these. Okay? Okay, folks, I have just one topic left from section 2.5, and that is, we've already looked at it, but let's just formalize these limits, infinite limits at infinity. Okay? What does the graph of the curve x look like? Well, it just looks like this, right? So if I asked you to give the long-term behavior as x goes to the right, what is its long-term behavior? As x goes further and further to the right, what do the y values do? They get arbitrarily large, right? So we would just say that that's infinity. What about as we go to the left? We approach negative infinity. What does the graph of x squared look like? Well, that's this parabola right here. So as x goes far to the right, what do the y values do? They become arbitrarily large. What if we go far to the left with x? Where are we approaching here? Infinity as well. What's the rule of thumb? I'm just going to jump to the rule of thumb. What's the rule of thumb here? If the degree is even, if it's just a polynomial and the degree is even as we go far to the right, we get arbitrarily large positive. And if the degree is even and we go far to the left, we also get positive. But if the degree is odd and we go to the left, we get arbitrarily large and negative. Any questions on that? Did I do that too quickly? We all okay? All right. So that's just what's summarized down here. Okay? All right.